Applying reinforcement learning to real-world robots is challenging for a number of reasons. Reinforcement learning often requires a substantial amount of data, which is time-consuming to collect. RL algorithms also typically rely on the environment being reset between every episode, which requires human intervention. Even when RL succeeds and the robot learns a policy capable of performing the task, the policy may fail to generalize to minor variations in the environment. In this paper, we present a robotic learning system called Ariel that uses offline multitask prior data to address the challenges of sample efficiency, non-episodic learning, and generalization. Ariel consists of two stages. In the first stage, we use offline reinforcement learning to obtain a policy capable of performing the tasks in the prior data. Then in the second stage, we use the policy to initialize online learning of a new task. To learn the new task autonomously, we initialize both the forward and backward controller. When learning the new task, we alternate between applying the forward controller to perform the task and the backward controller to reset the environment to an initial state. We use the data collected online, in addition to the prior data, to adapt the parameters of the forward and backward controllers with reinforcement learning. Optionally, if the new task is outside the distribution of the prior tasks, we can provide additional guidance by augmenting the prior data with a small number of human demonstrations of the new task. We evaluate Ariel on a pick-and-place tasks, where each task involves picking up an object and placing it into or on top of some container or object. We use a hand-engineered scripted policy to generate a prior data set of behaviors consisting of moving a wide variety of objects into and out of different containers. The scripted policies we use are imperfect, successfully completing the tasks approximately 30 to 90% of the time. Here we show the variety of objects and containers used in our experiments. Optionally, we can provide a small number of demonstrations of the new task by teleoperating the robot with a 3D mouse. These demonstrations are simple to collect and allow our system to adapt to tasks outside the distribution of the prior data. Note that the demonstrations by themselves are not enough to learn the new task. Next, we perform multitask offline RL on the prior data and optionally the demonstrations to obtain a policy capable of performing the prior tasks. After offline learning on the prior dataset, we perform autonomous online fine-tuning on a new pick-and-place task. Here, the task is to open the drawer and place the toy tiger inside. During the training process, Ariel alternates between applying the forward and backward controller to alternate between attempting to perform the task and attempting to reset the environment to an initial state. After only offline learning, the robot makes reasonable attempts at the task but does not consistently succeed. However, after 9 hours of mostly autonomous fine-tuning, the robot can consistently put the tiger in the drawer and take it out. Here, the task is to put the red block in the correct slot. After only offline learning, the robot frequently fails to grasp the block. But after 1.5 hours of fine-tuning, the robot can consistently put the block in the slot and take it out. Here, the task is to put the green ring on the peg. After only offline learning, the robot frequently misses the ring. But after 1.5 hours of autonomous fine-tuning, the robot can consistently put the ring on the peg and take it off. During the online fine-tuning process, the robot can learn new behaviors unlike those seen in its training data. Here, when removing the ring from the peg, the robot has learned to first move the ring to a more favorable grasping position and then attempt to remove it again. This retrying behavior was not seen in its training data. We also evaluated whether Ariel learns policies that generalize more effectively to varied conditions. We first evaluated the zero-shot generalization performance of a policy obtained after the fine-tuning stage of Ariel. Here we tested whether the policy can place an unseen object, the pickle, into the drawer. Ariel succeeds 5 out of 5 times. We compared to a policy trained on only single task data collected during the fine-tuning stage of Ariel. We found that this method succeeded only 1 out of 5 times. Lastly, we conducted experiments with a simulated version of our robot to compare to prior work and ablations. To validate the statistical significance of our results, we ran each method with 4 random seeds. We found that Ariel outperforms prior methods for reset-free reinforcement learning and learns more efficiently than methods that do not use prior data. In summary, Ariel leverages multitask prior data to learn robust policies more efficiently and with minimal environment resets, addressing key challenges in applying reinforcement learning to real-world robots.